So to get Green's theorem, you got to know your line integrals. So last time, what did we do? We did something called independence of path. And we found that if you're doing a line integral and it happens to be a conservative vector field, the line integral is automatically independent of path. In other words, you don't care how you got from point A to point B. Could be a straight line, could be a curve, could be whatever. You don't have to parameterize. That means you can get the potential function and use the potential function and a fundamental theorem of line integrals and do your line integral that way. Now, if your vector field is not conservative, then your line integral is not independent of path. What does that mean? You care very much about the path and what it looks like, and if it's curvy or a straight line or all this. And when you parameterize your curves, keep in mind, you definitely have to know how to parameterize. What does that mean? And so on your quiz, I found some of you still aren't clear on parameterization. You give me a vector valued function, R of t, and some of you used the letter S, and I took away points. Not okay. Well, why not? The letter S, if you use that as a parameter in your parameterization, traditionally that means you're using the arc length parameter to parameterize. And those of you that were using S's, you weren't doing that. And so not cool. Okay, well, what's arc length parameter? Go back 2 months and go review your course reader, because we discussed it, and we discussed parameterization involving the arc length parameter. And I don't want you wasting time trying to parameterize using arc length parameter. Please use the letter T. So if you have a 2D curve, you're supposed to come up with two functions, x of t and y of t, and then tell me what time is doing. I need to know the interval. And if you neglect to tell me the interval, then big problem. I take away points from that. Some of you went, well, I put the limits on my line integral. So that's how you know. Yeah, but I want it to show up right when you're doing the parameterization, because that's part of parameterizing a curve. Okay, you definitely need to know how to do that. And we'll do a little bit today just as a touchstone verification. Okay, so keep that in mind when you go over your quiz. And I still need to post those grades, and I'll do that after class today so you can review. So let's do a definition, a couple of definitions, and then we'll hit what Green's theorem is. So what do we need to define first? Because these are some conditions that need to be met before you can even use Green's. You can't just use Green's whenever you want. Certain things have to be in play. So first of all, you need what's called a simply connected region. What the heck is that? Recall that a connected region means that any 2 points in the region can be connected by a piecewise smooth curve lying entirely within the region. So in other words, not Hawaii, not Hawaii, because Hawaii is not connected. It's got different islands. You know, you got to leave one island to get to the other island. So it's not connected. Now, simply connected is a little more special. So here are some diagrams here. This guy here is simply connected. These other two regions, even though they're connected, they're not simply connected. So one of them has holes in it like Swiss cheese, and the other one has the boundary like twisting over on itself. That's not simply connected. Okay, fine. And then we're going to do this definition of a simple curve. A curve given by some vector valued function where time goes from A to B is simple if it does not cross itself. So in other words, if you evaluate it at any point, it's not going to equal some other value for different C's and D's. That would mean it twisted over and crossed itself. Okay, and now we can define what a simply connected region is. I mean, you see the pictures here, but how do mathematicians say that without pictures? So definition of a simply connected region. Here we go. Plane region R is simply connected if its boundary consists of one simple, and you just learned what a simple curve is, it doesn't cross itself, closed curve. And we defined what closed meant last time. It meant the starting and stopping points are one and the same because it goes, you know, it's closed. It starts exactly at the same place it ends. Okay, now you're ready for Green's. So what's Green's? Here it is. It says, first you need a criteria. You need your region to be a simply connected region with a piecewise smooth boundary. And then here's the weird part. It has to be oriented counterclockwise. So for those of you who like, what's counterclockwise? It's going the opposite of some clock hands. And these days, people don't even know what an old-fashioned clock looks like because everything's digital. It's like, well, I don't even know what clockwise means. I get it. But counterclockwise, opposite of clockwise. Okay, so you need it oriented counterclockwise. And we'll discuss that in a little bit with a joke, but you're not ready yet. Okay, so when you go around your boundary, your curve is traversing your region once, and the region lies to the left of your curve. So if you look up here to this nice, simply connected region, if you're driving in your car around the boundary of your region in the counterclockwise orientation, if you were looking over your left shoulder, I'm looking over my left shoulder right now, you would see your region as you're driving around. Keep that thought in mind when we do something later on today. You need to look over your left shoulder while you're driving, and oh, I see the region there over my left shoulder. Fine. So if that's the case, then if you have a vector field where M and N, so when we're talking about M and N, those are the components of your vector field. If those guys have continuous first partials, then if somebody tells you to go do a line integral that involves a closed curve, so that's where I put this circle around the line integral and then put a C down below, which means it's a line integral, you don't even have to do the line integral if all these conditions are met. You will turn it into a double integral instead. Aha, this is where double integrals come back into the conversation and why it was so important for you on the last midterm to really get those double integrals cold. And you're going to integrate a very interesting integrand. It's going to be the partial of n with respect to x minus the partial of m with respect to y over the region. Cool. That's greens. So what does it say in plain English? Well, this may not be plain English to you, but basically this double integral over this simply connected nice region determines the value of your line integral over the closed boundary. They're one and the same, which is kind of neat. So I'm going to do a half proof, and then we'll do lots of examples. Okay? So get ready. These are greens going here. So first, let's do a partial proof, and you can do the other half. It's just pretty much the same. Let me just draw a diagram here. Let's say you had some region, I don't know, let's say here's A, and it kind of went like that, and we'll call that curve 1. And then curve 2 kind of, you know, like this. We'll have it neat. This will be, I got to make sure I do this. Hold on. Got to have A here. And let's say curve 2. I'll even do a different color. What the heck? Curve 2 is like, I don't know, some other weird thing like that. There's C2. Fine. And I hope you can see that this region R is definitely a nice connected region, and it's simply connected because the border doesn't cross itself or twist over on itself or anything like that. So let's say curve 1 is given by some function y equals f1 of x. Fine. And let's say curve 2 is given by, I wanted to use a different color. Oh, boy, I'm really blowing it with my eraser. Woo! Okay, so let's say curve 2 is given by y equals some other function, f2 of x. Fine. So let's say somebody said, hey, I want you to do the line integral around that closed curve. So you'd go, all right, a line integral, mdx plus ndy. That's one of your vector field line integrals. And because you have two separate curves making up the entire curve, you have C equals the union of C1 and C2, you would actually be required to first find the line integral for C1 and add that to the line integral over C2 and would sum up the results and you get the final answer. So you'd have to do two separate line integrals. So let's go with that. So what would that look like? Well, this first line integral would be the integral going from, I didn't define what B is. Let's say B is over here, this endpoint. You'd have A to B. And let's just look at half. So we're only going to look at the MDX portions only, okay? And you can do the NDYs in a separate proof and then add the results. So let's say you had your M and you're going to do your C1. So you'll have X and the Y is F1 of X and then DX plus, and then the C2 goes kind of backwards. It starts here at B and then ends at A. Yeah, and remember I mentioned that you can have your limits going backwards if it matches the curve exactly. And somebody put a negative in front of there. No. You're not saying, oh, A to B, B to A. We'll do that in a moment, but somebody put a negative in front of their line integral and blew the whole thing out and got the opposite in sign, and I took away a lot of points. And you'll figure out who you are when you see your paper. So B to A, because we're starting at B and then we're going back to A along the second curve. So M will have X comma F2 of X. Okay, fine. So what? Now we'll use that handy fact that says if I want that to go from A to B, then I reverse it and then put the negative. So you got to make sure you do it in order. This guy stays the same. He hasn't changed. Fine. Now you have a minus here instead of a plus, and he's going to still have M at evaluated M F2 of X. Now, because both of these integrals have limits that match, and you're both integrating with respect to X, you can combine into one big old integral, which we're going to do right now. And so the integrand is M X comma F1 of X minus M X F2 of X. Okay, save that for later. Now I'm going to do the second part. So on the other hand, OTH is short for on the other hand. What about this double integral? And let's look at the M portion of it, the M portion here in the greens, which is a dMdy thing there. So what if somebody said, hey, go do the partial M with respect to Y integral over that region. And the region R is this region that's bounded by C1 and C2. Fine. Well, then you would go, all right, well, from what I know about setting up double integrals and their limits, because you went through chapter 16, if I choose dy dx to be my favorite order of integration, X is pure number to pure number, A to B. And then if I stick my little man in there in my region, since this is vertically simple, here's my little man, his top of his head is the upper limit for Y, that would be F2 of X, and his feet are touching the lower boundary, which is F1 of X. Fine. Now, from what you learned from Calculus 1, because you're all Calculus 1 grads, when you take an integral of a derivative, so we're going dm dy dy, what happens when you integrate a derivative? Don't those operations, aren't they inverse operations?
Yeah.
What do you get?
M.
Yeah. So you're going to go, hey, I'm going to just get the function M, which is a function of xy, and we'll evaluate it between the limits, which are the f1 and fx. And so we're still going to have to integrate with respect to x after all that's said and done. And then these get substituted in place of the y because we just integrated with respect to y. So then this is going to look like mx comma f2 of x minus mx f1 of x, like that. Now what? I want you to compare these two halves of this proof, essentially. I can't help you with getting blurry. Okay, sorry. Don't know what to do on my end. So what I want you to try to do, blurry or not blurry, is are these two things, that thing that I'm circling in red and the other thing I'll circle in pink, similar to each other or not? I claim they're similar and they're slightly different. Can you see the similarities and can you see the differences between those two things?
Yes. Yes.
Okay, so what's different?
The first term of the integrand.
Mm-hmm. So this thing is the same as this thing over here, right? Yeah, that's an f1 of x. And then these two are the same. So I claim that the pink one is really just the opposite of the first one, the integrand. So I'm almost done with this proof. So if you're following this, congratulations. So what I'm saying here is that this thing here, if I compare it to the other guy, what I'm saying is that the line integral m dx, that's the one I have in red, is going to be equal to the opposite of the double integral over the region dm dy. And that's kind of where the minus dm dy comes from. So if you look at greens, you'll notice, oh, it's minus the dm dy. And you can do a similar thing with the ends, and the ends end up being exactly the same. You don't have to do a minus when you compare the line integral to the double integral. So I'll leave the rest to the reader, and we're done. So there's the end of the proof for greens. And now let's do some greens. Okay. So I think what I'm going to do is I'm going to do letter B, and then I'll go back and do letter A. We're going to do this a little out of order because the verify is going to take some time. Well, I don't know, maybe we should just go ahead and do it. Yeah, let's just go ahead and do letter A. It's going to take some time. So anytime you're asked to verify something, any theorem, if you're going to be asked to verify, that means that you have to do the left-hand side of greens and the right-hand side and show they're equal. Okay? So that's what a verify means. So anytime you see verify, you should go like this. Oh man, I got a lot of work to do. Yeah. So I'm gonna do the hard one first. So let's do the left-hand side, which means pretend you don't even know greens, and you basically are gonna have to do the line integral brute force. So this is a good review, though, especially if you didn't do so well on the quiz on Monday and you feel like I still don't get line integrals. It's a mystery wrapped inside of an enigma. Please stay awake right now because this is basically review. Okay, we're going to do the line integral by brute force. That means we're going to have to parameterize all over the wazooby and do all the things that you have to do when you do a line integral by force. Okay, now before I start doing this long example, remember that if this is a conservative vector field, heck, I don't have to do any brute force line integration because I don't even have to parameterize if it's conservative. So maybe we should ask this question real quick. Is this a conservative vector field? Yes or no? So the m is y cubed. What is dm dy equal to? What's the partial of y cubed with respect to y?
3y squared.
Sure. And then dn dx, what is the partial with respect to x of x cubed plus 3xy squared?
3x squared plus 3y squared.
Yeah, so are these two things the same?
Absolutely not.
No way. So sorry, it's not conservative, so you can't use the fundamental theorem of line integrals to evaluate that line integral. Nah, bummer. Okay, so what are we going to have to do? The hard way. So we're going to do the left-hand side of greens right now. There's no double integrals involved. We're going to actually do the line integral using all of our knowledge from the last couple weeks of line integrals. Okay, so what does the curve look like? Well, there's two pieces, which means we not only have to do one line integral, we're going to have to do two and add the results. Oh, bummer. Yeah. So the first thing it does, if you read the directions, it says it goes from the point 0, 0 to the point 1, 1 along the graph of y equals x cubed, which has a little bit of a curve to it. So it's not a straight line. And then it's the reverse. So that's like C1, if you will. And then oops, sorry, this is the 0.11. And then it goes backwards. It starts at the 0.11 and goes back to 0, 0 along a straight line. So we'll call that C2, which is y equals x. Okay? So the LHS, the left-hand side of Green's, is saying, hey, go do this line integral with differential form, but you can still do FDR. It's the same thing. But I claim we're going to have to do two separate line integrals, one for the C1 and then another one for the C2, and then we'll add the two results together. So this is going to take some time, but it'll be worth it because, you know, review is good. So let's do this guy first and do everything that needs to be done just to do that guy. So if you'll notice, the C1 is along the curve y equals x cubed, and I'm going to parameterize because I think some of you need some review on that. So how do you parameterize y equals x cubed, where you're starting at 0, 0 and you're stopping at the 0.11? Well, since it's a function of x, and I already taught you how to do this, what's the easy peasy way when you have a function of x?
Let x equal t.
Very good. You just let x equal t. And then since y is equal to x cubed, y is equal to what?
T cubed.
T cubed. And then pick a time interval that's going to match this portion of the curve for this parameterization. What time should I plug in to start me at 0, 0 and finish me at the 0.11?
0 to 1.
0 to 1.
Okay. Are you guys still having problems hearing me or seeing me?
We can see you just fine. Is that like intermittently the screen will like lose resolution?
Okay, so here's what I'm going to do. Let me stop share for a moment. And so when I do a share screen, when I was doing the burbs, let me uncheck optimize screen sharing for video clip. This might fix the problem. Let's see.
Yeah,
Okay,
that's good.
it's good.
Okay, it doesn't look like it's recorded with a potato anymore.
Okay, that's better than Nick. Recorded with a potato. I love it. So this is the parameterization. Notice I'm including the time interval. I'm going to go get R prime because you're going to need R prime to do the line integral using brute force. Okay, so the derivative of t and t cubed is 1 and 3t squared respectively. This is going to be basically be the dx portion when we multiply it by dt. This will be the dy. You replace x's with t and y's with t cubed. So this integral y cubed dy plus the quantity x cubed plus 3xy squared dy is going to turn into the integral going from 0 to 1. And so y cubed dy, we got to be careful here because it's going to be a hot mess. It's t cubed cubed. And then that's supposed to be a dx right there. Multiplied by dx, but that's just 1 dt, plus the quantity x cubed plus 3xy squared. So x is t, so t cubed plus 3 times t cubed squared. And then the dy is replaced with 3t squared dt. So this is what you're going to integrate with respect to t. Now this is a calculus 1 problem, people. So don't blow it. You do have to know some exponent laws though, so don't blow that. That's a common student error. What's t cubed cubed? Is that t to the 6th or is it t to the 9th?
No, t to the
9th.
T to the 9th, good. So you're going to go t to the 9th plus, and then I need to distribute this 3t squared over the sum before integrating. So I'm going to have t cubed times 3t squared. Is that going to be 3t to the 5th or 3t to the 6th?
The 5th.
Yeah. I'm just checking. And then this, we got t cubed squared, that's t to the 6th, times another power of t, so that's t to the 7th. And then you're going to multiply it with t squared, and then you have the 3's in there also. So I think you're going to get 9, t to the 9th. And you can integrate this right now, or if you prefer, you can combine like terms. You know, I like to always combine my like terms just to make it a little more clean. And then you integrate that. Okay, so what are you going to get? 10 over 10. I get t to the 10th plus, I think it's a half t to the 6th, then you're going to evaluate between 0 and 1. And I get 3/2. That's not the answer, but you can save it for later. Why? Because we're still in the middle of doing that line integral, and we have the other half to do, the C2. So I still got more work to do. Oh, man. Okay. So now what? Well, if I'm going to do the line integral now along the curve where I start at the point 1, 1, and I go backwards, I go back to the point 0, 0. Okay? So here's what I'm doing. I'm going to do the line integral, but C2. So I need to parameterize C2 though. Well, good news, it's a straight line where y is just equal to x. So it's a function of x, so I'll let x be t, and y is equal to x, so y is t. Now here's the part that I let you do that some professors don't. I'm just letting you know, because some of you may have friends in another class, and then you might be arguing, hey, my teacher doesn't let me do that, and then you could duke it out. Okay, I let you have your time go backwards. So in order to make this match what our curve is doing, because orientation matters, my time is going to start at 1 second and finish down here at 0 seconds. I know that seems weird, but it's going to work. It's legit. Now, if you do have a professor who's like, well, I'm not down with that, I'm going to take away all your points. I just want to say there is an alternate way that you could parameterize this where your time isn't going backwards. So let's say you had a teacher who's like, hey, I got to have time moving forwards. No such thing as time moving backwards. Can't turn back the hands of time. You're like, oh man, why not? I like reliving my junior high years.
The rewind button on my VHS player would like to say something.
Yes, I totally understand. And I'm sure you're still watching VHS. Oh, that's awesome. My parents they're getting up there in years, so they're cleaning out their condo, and they're handing me all these old things from my past that they no longer want to store. And I kind of don't like this because they're in their 80s, and I feel like they're going to check off the planet when they start, oh, we've got some of your old, and I'm like, oh no, Mom. So they gave me my old 8th grade yearbook from junior high. I'm like, no, oh my God. My dad's like, yeah, oh my God. Fun times. Okay, so if you were going to do a different, we'll call this R2. Let's say you're doing a different vector valued function that isn't going to have time. I'm going to use mine, okay? But I just want to let you know, how would you do it? Does anybody have any guesses on what they would put in for their x of t and their y of t components here for their vector valued function if time had to move forward from 0 to 1?
Not off the top of my head, no.
Okay, I'm gonna teach it to you right now. Since we want x coordinate to start at 1, and we want y to be 1 also, but y is equal to x in this case because we have a straight line. If I plug in 0 seconds, I want the x coordinate to be a 1. So what if I go 1 minus t? Won't that work? When I plug in 0 seconds, won't the x coordinate start at 1? Say yes.
Right. Mm-hmm.
And then since y is equal to x on this particular curve, y will just be 1 minus t also. Now, if it weren't, let's say y was equal to, I'm just going to make something up, square root of x, just say it was something different, then your y would be square root of the 1 minus t. Yeah? Hello?
Yeah.
So this will work also, but you have to go get that r prime and everything. I'm just not going to use it, but I'm going to say it's totally legit. We'll end up with the same answer, believe it or not, because parameterization doesn't affect the outcome of a line integral. Orientation does. Now, if you do your parameterization where you plugging in your time, the curve moves in one direction, but the problem is asking you to go in the opposite orientation, you're going to be wrong. Okay, so here if I get the r2 prime, that's pretty easy. It's a constant vector, so there's your dx and there's your dy. And so now when I do this line integral on C2, y cubed dx plus, I told you this was going to take a long time. Holy guacamole. We're doing this line integral. What does this line integral become? Sorry. Boy, do I hate these Microsoft Surface Pros. It becomes the single integral going from 1 to 0, because that's how I'm rolling here, 1 to 0, a y cubed, for us that's t cubed, dx is just 1 dt plus x cubed, that's t cubed plus 3xy squared, that's 3 t t squared, and dy also happens to be 1. And so you're like, okay, what's all this stuff? And this is t cubed, and this is another t cubed. This is 3t cubed. I claim those are all like terms. Cool. Add them all together, and you get, hey, let's just integrate 5t cubed. That's not too bad. All right, fine. And the antiderivative is 5/4 t to the 4th, and you're going to evaluate it going backwards, 1 to 0. Yes, it matters. So first plug in the 0. Well, that'll be 0. Minus, and then plug in the 1, and I just get 5/4. So I get negative 5/4. So what's the total final answer for this problem? The final answer is the first answer we got. Shoot, I forgot what it was. Okay, it's up here. 3/2. Come on, PDF, you can do this. Plus negative 5/4. And what the heck? I think that's going to end up being 1/4. And we're done. That's the value of the line integral. And we did it the slow, hard, brute force, pain in the rear end method. Yay, but we got an answer. Woohoo! Success. Now what? Now, since you're in the middle of verifying Green's theorem, let's recap what we just did. What we did when we were doing this verify is we verified that the left-hand side here in this theorem, don't scroll anymore, is equal to 1/4. Yay, us. Now, let's do the right-hand side and prove it's going to give us the same thing. Fantastic. So we're not going to do any line integrals because we're going to do the right-hand side.
Hello.
Oh no.
Yeah.
Uh-oh. Well,
Wait, she's still going?
I'm sorry, folks. I bombed out. Where did I bomb out? I apologize.
gone. No more.
Can you hear me?
Give it a second. Nope.
Wait. No, wait, no. Almost.
Can you hear me?
Yeah.
Hello.
Okay.
Yeah, no, I can
Yeah.
totally not hear you.
Lagging out.
I can hear you.
Can you hear me
Everybody
okay now?
just lagged out.
Can you hear me okay now?
Yes, you're good.
Yeah,
Yeah.
we can hear you.
I'm coming in through the waist. Yeah.
Okay. So where did I drop out with my crappy internet?
The right-hand side.
Okay. So did you guys get the left-hand side though?
1/4, right?
Yeah.
So now we're like, we hate line integrals. It's so much hard work. Let's do the double integral. Is that going to be like as much hard work? Oh, you're going to love this. Now, this is the power of greens. You're going to be so happy. I'm going to put a smile on your face in about 2 shakes. Here's why. This region here, there's your region. I'm coloring it in. Hopefully you can see it. That's the region R that we're going to set up a double integral on. Okay. It's a little sliver, not much. But what we're going to be saying is when we do the right-hand side of greens, so we're going to do RHS, right-hand side, it says do the double integral instead, but your integrand is going to be dn dx minus dm dy. Okay, now good news, I think we already figured out what dn dx and dm di were when we started the problem because I was asking, hey, is this conservative or not? So back so we don't have to figure these out again. Dn dx was 3x squared plus 3y squared. That's good to know. And then the partial of m with respect to y was 3y squared. Cool. So that's going to be our integrand. We already figured all that crap out. Excuse me. So that's going to be 3x squared plus 3y squared. And then minus, and then our dm dy happened to be 3y squared. Yeah? Can the 3y squareds cancel here? Yeah. Yeah. Gone. Sorry, you're out. Oh, cool. So what's the only thing that we're going to have in the double integral for the integrand? 3x squared. That's nice. Is it always that easy? No. Now, what about dA? Well, that's where you get to pick what order of integration you like to do. What's your favorite? I personally like dy dx if I can get away with it. Fine. Go back to your region to help you iterate the double integral. And let's do the outermost integral first, since that's always pure numbers, constants. What constant to what constant is x doing on this region here?
0 to 1.
0 to 1. Okay, so you can like put something on your double integral here. We're getting closer. We're getting closer. And now what about y? No, don't tell me y is going from 0 to 1, because then that tells me you didn't learn anything in the last month. Okay?
X cubed X.
Yeah, if you look, if you stick a tiny little man here, he's really super tiny, he's standing vertically inside the region. His head is touching the upper limit, which has the equation y equals
X.
x, and his feet are located on,
X cubed.
yeah, so your upper limit is x and your lower limit is x cubed. Fine. Now, you know, use your knowledge of double integrals. Here we go. What is the antiderivative of 3x squared with respect to y?
X squared y.
So you're going to evaluate the y between these limits, and that's not too hard. You guys are pretty well versed at double integrals at this point in time, I hope. Like so. And then I'm going to distribute the 3x squared before I keep going, and I'll have this to integrate. And this is super easy because this is just a Calc 1 problem. No worries here. And I'm not doing anything crazy. And so, all right, I think this is going to be 3/4 x to the 4th minus 3/6, but that reduces to a half. X to the 6th, evaluate that puppy going between 0 and 1, and I get 3/4 minus a half. Oh my God, I get a 4th. And that matches the left-hand side. Whoo! Thank God. So which side do you think was easier to do? The left-hand side, where we had to parameterize twice and do brute force 2 separate line integrals and add the results, or one double integral?
Do I even need to say it?
I know, that was the whole point of that problem. You're supposed to go, wow, greens is awesome. So let's recap. Brute force versus easy peasy double integral. Now I will say that you do have to have some criteria met. Like you can't just use greens whenever the heck, you know, oh, I'm not going to do any line integrals from here on out. You know, line integrals are going to be against my religion. Ha ha ha. Well, big problem with that, because line integrals are only allowed to be done, greens rather, can only be done with if your line integral is being evaluated over a closed curve. The curve has to be closed. If it's not, forget greens. The region has to be simply connected, and you have to have a nice vector field where the components are, you know, nice continuous partials. So if all of those conditions are met, greens, baby. Greens. Okay, so now let's do some more examples. Let's keep going. Where the heck am I? Oh my goodness. Okay. Okay. Does a vector field need to be conservative in order to use Green's theorem? Yes or no?
No.
No. In fact, if it were conservative, what would the answer be?
0.
0. Yeah, you wouldn't even bother using greens or anything, because remember the equivalent conditions on Monday's lecture, that if you have a closed curve and your vector field is conservative, don't even bother doing any work. The answer is 0. So don't waste valuable time doing greens if dm dy is equal to dn dx. Because if you look at greens, let's just go back there. I'm trying to make a point here because I see students who are new wasting valuable time on an exam, you know, doing silly stuff. And you don't want to be wasting time doing silly things when you could be moving on. So look at this double integral, this Green's double integral. Do you notice that if dm dy were equal to dn dx, which means the vector field's conservative, this integrand would be one big fat 0?
Oh, yeah.
And the double integral of 0 is 0. So don't bother. Just cite the equivalent conditions theorem from last time. Just say, hey, equivalent conditions theorem says you got a conservative vector field. That's equivalent to saying every line integral around a closed curve will be 0 no matter what the curve is. So this is key that you get that so that you don't waste valuable time. Okay. So now Let's keep going. How about you guys do one? You want to try one?
Let's do it.
Sure.
Do it. Let's do it.
Sure.
Come on, guys. Look alive, will ya? All right, I'm going to put you in breakout room. So you and a buddy are going to do letter B here. All right. It's not that bad. I just taught you how to do it. Now, here's the thing. Don't do a verify, though. You don't have to do the left-hand side. Just immediately apply greens. Now, here's a tip, though. I have a little blank graph over here. It might be good for you to graph the region, okay, first, so that you don't blow it when you're iterating your double integral. Iterating means sticking those limits on there. You don't want to blow it or have it backwards or some other such yuckiness, right? So let's put you in rooms here. All right. I'll see you in a moment. Bye. Okay, so hopefully what you did first before you did anything is you graphed y equals 2x. Okay, I don't know, get a couple points going here. Woo, there's y equals 2x. Okay, and then you graph y equals x squared. Oh boy, got a nice parabola going here. And they do intersect right there at the point 2,4. And you got a nice region here. Now it's understood this is a simply connected region. And if we did have to do a verify, which thank God we don't, but if we did, we would have to parameterize this first leg of the journey because you have to go around counterclockwise. That would be C1. We do a line integral by brute force and have our curve go starting at 0, 0 and ending at 2, 4. And then we'd have to parameterize, the journey back to the starting point, call that C2, and that's along the straight line y equals 2x. And we'd have to parameterize it in such a way where it begins at 2, 4 and ends at 0, 0. We would add those two line integrals results and we get the final answer. Yeah, that will take a long time. Instead, woohoo, forget that. I'm going to do a double integral, which is going to give me the same answer as those two line integrals summing up. This is easier, much easier, because it is a closed curve. And, we can assume that the, orientation is counterclockwise. Okay, fine. Now what? I got to put a note to self over here because I need to tell you about two things here. Number one, work. Number two, Dr. Leslie. I got to tell you a joke. Okay. Make sure I do these over here. Okay. Okay, dn dx. What is dn dx? Okay, let's set it up. Well, n is x cubed. So what is the partial of x cubed with respect to x? Quick.
X squared.
Very good. Minus, because the theorem says minus dm dy. So m is 5xy. What's the partial of 5xy with respect to y?
5x.
Yeah. So boom, there is your integrand. Great. Now what? Well, now it's time to your dA. Do you want to pick dy dx or do you want to pick dx dy, your order of integration? It's up to you because either one would be fine.
dy dx.
That's my personal favorite. Good choice. Okay, now let's iterate the outermost integral because that's always going to be constant. So what constant to what constant is x doing on this gorgeous region here?
0 to 2.
0 to 2.
Yep, 0 to 2 is correct. Okay. Now what's y doing? And please don't say 0 to 4 because that ain't happening. If you put a little man in here, here he
X
is.
squared to 2x.
Yeah, your x squared is your lower limit. That's his feet. And then his head is on the straight line, so 2x. And so if you got this far, I always give partial credit for the setup. So congratulations if you set it up correctly. Now let's see about the answer. Oh dear. So all this integrand is only, an expression with x. So if you're integrating with respect to y, that's easy peasy because that just looks like a constant multiple. And you're just going to have your y going between x squared and 2x. Okay, fine. Always plug in your upper limit first. Don't forget. Now, this is the part where some of you might have screwed up. I don't know. But after doing that, if I were you, I would FOIL. You guys know how to FOIL? Hello, FOIL?
Yeah.
Wouldn't be
What's it?
true otherwise.
What's
Yeah.
it?
I mean, you're not going to try to integrate this without foiling, okay? And yeah, this is kind of a, a pain in the butt. Yikes. Okay, so 3x squared times 2x, I get 6x cubed. 3x squared times minus x squared, that's a cube, that looks terrible, minus 3x to the fourth, and then negative 5x times 2x is negative 10x, and then negative 5x times negative x squared is positive 5x cubed. Everybody got this?
Yes.
You can integrate this right away, or if you prefer to combine your like terms, which I always do because I like, otherwise I usually blow it. So I'm just going to first combine those x cubed terms together, and now I'm going to integrate. I get 11/4 x to the fourth minus 3/5 x to the fifth.
That should be a 10x squared.
10x squared, thank you. I was just looking at my notes too. I was like, hey, where did the squared go? And then the antiderivative of minus 10x squared is minus 10/3 x cubed. Yeah?
Yes.
And you're going to evaluate that between the limits of 0 and 2. And then you plug it all in, I get negative 28/15. Oh dear, are we allowed to get a negative answer for double integrals? You told us that was forbidden. I only told you that if your double integral represents a volume, or if your double integral represents a surface area, or if your double integral represents mass. If any of those three things are happening, you better get a positive result. However, this is not that. So negative answers are okay. Let's visit that. So I'm now covering note 1, the self. So hopefully if you really got Green's theorem, and I know it's new, so maybe you didn't get it for yourself, but I want to go back and revisit it so you are sure of what it says, because I might ask a true false question about it. Okay. When you're doing a line integral, the application of this kind of line integral for our physics brethren is a work. It can represent work done. It also can represent circulation, which we'll hopefully have time to talk about today. I don't know. So remember, in physics, when you're computing work done on an object as it moves around in some vector field, the answer could be positive, can be negative, or 0. Any of those three things can happen. And so since we're saying the line integral is exactly equivalent to this particular double integral, the double integral result can be positive, negative, or 0. So when you're doing Green's, you may get a positive, a negative, or a 0, and that's fine. Okay, so that's legit. Any questions on this? Did you guys all get negative 28/15?
Yes.
Sorta, kinda, maybe not. Okay. The other thing I wanted to say is a quick joke. When I first started teaching this course back in 2000, a student said, well, hey, they raised their hand. They're like, hey, Green's, it's only okay on counterclockwise oriented curves. And I said, yes, that's right. And they said, yeah, but what if I want to go clockwise, And and I said, basically you're going to get the wrong answer. You'll get the answer, but it'll be opposite in sign. Okay, that just because of the nature of the way Green's is happening. So, and there is some right-hand rule stuff to it. I don't want to get into that now, but Stokes will get us there later. So that's kind of why. But then I went to my advisor, who I was still in contact with at the time, who helped me with my thesis, my master's thesis at State. His name's Dr. David Leslie. And I called him up. Hey, Dr. Leslie, how do I answer a student's question? What if, it's oriented in the reverse direction? And always a kidder, Dr. Leslie went, well, I hear they do it in the opposite way in Australia down under. And you don't get the joke, supposedly that when you flush the toilet above the equator, the water whooshes in one direction. I don't know if it's counterclockwise or clockwise, but if you flush the toilet down under, below the equator, like Australia, it whooshes in the other direction. Do you get it? Never mind.
Did you coin the phrase whoosh, or did you learn that?
I coined it on my own. I have a lot of weird language you don't want to know. If you come to my house, I speak in bird language over here. Okay, so now I did my joke. Okay, using Green's to calculate work. And of course you can use Green's to calculate work because it's a line integral that you're doing, but you're not doing the line integral. You're converting it to double integral. So work is equal to a line integral and FDR or MDX plus NDY. And it is going to be a closed curve. Otherwise, we're not going to be able to do green. So I'll put a little circle there. And we're traveling counterclockwise around a circle radius 3. Now, on the quiz the other day, I asked you, I think there were 1 or 2 of the problems on the quiz the other day where you had to parameterize a circle. And some of you got it right. Congratulations. And so if you're parameterizing a circle centered at the origin of radius whatever, it's always easy to parameterize it. It'll be whatever r cos, radius of r cos t, r sine t, where t goes between 0 and 2 pi. Will always give you a circle oriented counterclockwise. Well, how come we couldn't use greens on the quiz? You actually could have if I had said it was okay to use greens if it was a closed curve, but you didn't know greens, so you couldn't use it. Ah, ha, ha. Okay, so I'm not going to actually parameterize or any of that jazz because I don't need to. I'm going to just apply greens. And green says, hey, don't even bother parameterizing. There's no need. If you've got a closed curve, that's good enough for us. Fantastic. Then what? There's your vector field. You need to get dn dx and dm dy. I'm going to do this pretty quick. The region is a circle. There's n, x cubed plus 3xy squared. So the partial with respect to x is going to be 3x squared plus 3y squared. So there's your dn dx minus dm dy. Well, the partial of y cubed with respect to y is 3y squared. And yes, these 3y squareds cancel. That's a beautiful thing. And then you're like, well, what do I have left? I just have 3x squared. Oh, okay. And then it's around a circle. So guess what I'm going to do? Convert to
Polar.
Yeah, you bet. So what do I know? Well, if it's a circle centered at the origin of radius 3, what's my r and theta limits going to be? This is easy peasy. You just got done with the midterm last week.
Your r is going to be 0 to 3, and your thetas will be 0 to 2 pi.
Perfect. So here's your limits on your double integral. And here you're going to have to convert 3x squared by brute force using a conversion formula. X is r cos theta, remember that? And then dA is be a pirate.
R d theta.
R dr theta, thank you. See, all that polar is coming in handy, people. Yeah, it doesn't go away. Yeah, all that stuff that you learned in the last chapter, it ain't going away because you're going to need it. Okay, so before I integrate with respect to r, I better square these r's and then combine all my r's into one big old r. So I'm going to have 3 cos squared of theta. And then when I combine all my r's, I'll have r cubed. So now I can integrate with respect to r. Fine. So I'm going to have r to the 4th over 4, and I'm going to evaluate that between 0 and 3. 3 to the 4th power, I believe, is 243.
Isn't it 81?
Well, hang on. It's excuse me. It's 81. It's 81. But I'm going to multiply it with this 3 over here. So 3 times 81 is 243. And then this is what I have right now. And we're going to do, this is a Calc 2 problem that my Calc 2 students hate me for. But for those of you who had me for Calc 2, what do we do to cos square to integrate it?
Power reduction.
Power reduction.
Power reduction formula, you bet. You know. And so 1 plus cos 2 theta over 2. And I always like to take the half out. So I only have to worry, I'm going to put 243/8. So I only have to worry about integrating the 1 plus cos 2 theta, and that's going to be theta plus a half sine 2 theta. And when I evaluate that between 0 and 2 pi, the sine term doesn't contribute anything. He's 0 both times. So the only contributor is the theta. So he's the only one helping us out here. That's going to give us a non-zero result. And after reducing the lowest terms, I get the work done is 243 pi 4. So I don't know enough information to do the units, so I'll just leave it. Okay. So there you go. You can use greens to calculate work. That's the point of that problem, as well as it's still okay to convert to polar if your region of integration is a polar sector, which includes circles or portions thereof. So that's a nice example, and that's why I put it in my lecture notes. Okay, keep going. Now we're going to get weird. What if your region is not a circle, it's an ellipse? Oh, man. And if I had to graph that ellipse, I would first divide both sides by 36 to get it into standard form. where there's a 1 on the right-hand side. And some of you, when you were doing your vector fields on your quiz, you forgot to do the step 1 that I like to see, which helps you limit how many points you have to evaluate when you're doing a chart. Some of you said, oh, it's circles all the time. Well, it's not. Sometimes you get ellipses as your level curve. So if you graph this ellipse, the x-intercepts are the square root plus or minus the square root of 9, which is -3 and 3. And the y-intercepts are plus or minus square root of 4. And so here's your ellipse. That looks pretty sad. Anyway, it's a nice region. It's simply connected. And it's a closed curve. So, hey, I don't even have to do this line integral. Screw it. I'm just going to go, hey, let's do a double integral instead, because we can. Okay, fine. Then what? Well, what is dn dx minus dm dy? So n is x squared plus y squared, right? So what's the partial of x squared plus y squared with respect to x?
2x.
Yeah. Minus, and now here's m. What is the partial of 2xy with respect to y?
2x. Oh, is it
Oh,
conservative?
it's conservative. So the final answer is 0. Done. 0. Yeah. So just recall, when you evaluate line integrals that involve conservative vector fields around a closed curve, you're always going to get that a line integral around a closed curve with a conservative vector field is equal to
0.
0. Thank you. Okay. Keep going. I hope I convinced you that I don't want you to waste valuable time if somebody says do a closed curve line integral with a conservative vector field. I mean, you're done. The answer is 0. Just cite the theorem of equivalent conditions and get the heck out of there. Don't waste valuable time. Well, I'll go find the potential function. No, like stop that. Like even if you get the right answer, I'll just take away points for wasting time because you're not getting it, you know. Okay, now this looks really hard because, oh my God, look at these crazy components for our vector field. Oh my God. And we still have the same ellipse here. Oh my God. You know, we've got this ellipse here. And there he is. So it's a nice region and it's a closed curve. And we're assuming we're going around the ellipse counterclockwise. We're all good. Make a double integral and watch what happens. Okay. And then you're going to learn something here. You're going to learn yourself something. If you don't learn anything today, I'm going to teach you what the area of an ellipse is. Watch closely. Okay. Here's n. What is the partial of that guy with respect to x?
1, right?
1.
It's 1. Right. It's just 1. Minus, okay, here's m, e to the negative x squared over 2 minus y. What is the partial of m with respect to y?
Let's say n. -1.
-1. Okay. Everybody with me so far?
Yep.
Okay, this is not a trick question. Not a trick question. What is 1 minus -1?
2.
2.
Okay, just checking. I'll have to look at that later, Nick. I get a 2. Okay. Now, here's the hard part. A lot of people might say, well, convert to polar. Bad idea. Really bad idea. Why? Ellipses suck. Like they're not really good candidates for polar. I mean, you can if you like paint, but I prefer circles and ellipses are not that. So please
Mike.
mute. Mute.
No, Rick.
Rick, he's got a lot going on at the house. So what I'm going to show you, and they do this all the time in physics, so pay attention because all you physics buffs, you're going to do this a lot. They like to, it's the easy, cheesy, sleazy way out, and I'm going to let you do it, okay? I don't always let you do this, but I am here. The 2 is just a constant multiple, so pull it out of the double integral. That's legal, fine. Now what? What did I teach you about a double integral that has a 1 as an integrand? What does it represent?
It's the area of the region.
Area of
Yeah,
the
it's
the region.
area of a region. Absolutely. Yes. So screw setting up the double integral and the limits. Don't bother. Because all you need to do is you're going to go 2 times the area of the ellipse. And you don't need to do no stinking double integral. You just have to know how to find the area of an ellipse. Oh man, well, how do you do that? Well, I'm going to teach you something kind of cool. If you have an ellipse, and let's just assume it's centered at the origin, but it doesn't have to be, okay? If you have minus A, and then B, and minus B is these intercepts, the area for your ellipse is going to be pi AB, where A is the distance from the center to the outer boundary along the X, the horizontal axis, and B is the distance from the center to above or below, on the vertical axis, okay, pi AB. So what is the area for us when we had this ellipse up here, which I drew? Look at this ellipse right here. What's A and what's B equal to?
3 and 2.
3 and 2 respectively, exactly. So you're going to go 2 times pi AB, and so for us that's going to be 2 times pi times 3 times 2, which is 2 times 6 pi. Final answer, 12 pi. Boom, I didn't even have to evaluate any double integrals. And physics folks do this all the time. Like if you have a circle and you end up with a double integral and it's an area of a circle, don't even bother converting to polar, just what's the area of a circle? You learn that in 5th or 6th grade. Use it. It's great. Okay, questions?
Wow.
Wow is right.
That wasn't even a question.
Yeah, very cool. So you're allowed to do that. Now, the fact is, even though Green's claims they need a simply connected region and all that, that's slightly a lie. And it turns out you're allowed to use Green's. You can extend it if your region looks like Swiss cheese and has some holes in it, which means it's not simply connected. But you have to be careful because you still have to integrate over the entire boundary. So let me just draw you a picture, and you'll probably see this somewhere if you take complex analysis also, so it's kind of worth doing. Let's just put one hole in the middle, but it's true for more than one hole. So this is a hole right here, okay? So watch how we allow this, because you can't just do whatever you want. Like, I'm going to break the rules and it's okay. Well, okay, fine. But so the first thing you're going to do if you have to do go around all the border is notice there's really 2 borders to this region. What do you mean? You got the outermost border, but then you also have a border around the hole. So this is how you work it, okay? Let's say here's the starting point, just for fun. And it's also going to be our ending point as well, because we still have to start and end at the same spot. That hasn't changed. Green's requires a closed curve. But what we're going to do is we're going to go all the way around the outside border, counterclockwise, and we'll call that C1. Then what? Once we get back to where we started, we have to head toward the hole because, we're going to have to go around that border. So you're going to make a slit. You're going to take a knife and you're going to cut. This is called a slit. You're going to cut a little line with a knife right into your region. Yeah, okay. So that's what you did with your knife. Okay. Then what? You're going to go along the slit down into the hole. We'll call that C2. And then once you hit the hole, you're going to actually go around the hole in a clockwise fashion. Well, you lied. You said it had to be counterclockwise, you hypocrite. No, remember, I specifically made the point that when you were driving around your region, you had to be able to look over your left shoulder, hey, left shoulder, and still see your region. So I claim the reason why we're going to go around the hole, we'll call that C3, in a clockwise direction is when you're driving around here, you still have to be able to look over your left shoulder and see land here, okay? Then once I get here, I have to head back home. So this curve here, I'll call it C4 and gets me back to where I'm starting. So the curves, and if I had to do this using line integrals, I'd have to do 4 line integrals. C1, union C2, union C3, union C4. Oh my God, please don't make me do 4 line integrals. Now, the good news is 2 of these line integrals would cancel each other out. Which ones?
C4 and C2.
2 and 4.
C4 would cancel C2 just because they're going along the same path, but in opposite directions. So these guys would, you know, add up to 0. So we'd only have to worry about the C1 and the C3. Okay. So that is how holes are going to be okay. All right. So I think what I'll do is I'll save this for next time, and I'm going to go into doing some hole business, and then we're going to do divergence and curl on Friday, which is going to be on your quiz also. So this week's quiz is going to be a little hellacious because you've got 17.3 independence of path with the fundamental theorem of line integrals, 17.4, which is greens, and then we're going to do 17.5 Friday. We'll wrap up greens. But before you leave, let me leave you with one thought, because one of the students asked me a question in the breakout room, and I want to kind of finish so that they get this for themselves. What is greens representing? Well, greens could represent work done around, you know, the curve, you know, as it is inside some vector field. But also, too, what I want you to get is when we're going to learn another version of greens next time also, the flux version. But right now, you just know the circulation version. So the circulation version, which we just did, it basically, whatever number you get, it can be positive, negative, or 0. And it can represent how fast a paddle wheel spins inside of a jacuzzi. What? So if you can imagine your vector field being a velocity field of some water in a jacuzzi, whooshing around, whoosh, there's your vector field. And you stick a cute little paddle wheel into this jacuzzi. It has to be kind of a very shallow jacuzzi because it's really supposed to be a 2D vector field. The number that you get when you do the line integral, if it's positive, that means that the little paddle wheel, can you see that with the little vertical paddles, will spin in the counterclockwise direction. And the value you get gets how fast it's going to be spinning. So if you get a very large positive number, that little vertical paddle wheel is just spinning up a storm. If you get a negative number, it just means your little paddle wheel is spinning in the clockwise direction in your jacuzzi. If you get 0, it means that your little paddle wheel is not spinning. Okay, he's just sitting there in the water, minding his own business. So that is a nice way to interpret this circulation integral, and that's the circulation form for greens. We'll do the flux version of greens next time, but I think this is a good place to end the lecture. Bye.
Bye-bye.
See ya.